All right, everyone. Thanks so much for having me. I'm so glad to present to you the decentralized NAT hole punching. I mean, NAT hole punching has been a common theme over the last few presentations already, and there's a specific protocol that the guys implemented, which is called DCUTR, which I will get to in a second. And I was working on a project on measuring the success rate of this hole punching mechanism. And in this talk, I will briefly discuss how hole punching works, and specifically the DCUTR protocol, then how we intend to measure that, so our measurement setup, and then the fun part, all the different graphs and results from that, and also then some next steps going forward. All right, hole punching. So what's the motivation? Oh, sorry, no, first a shout out to Max, who did great presentations on this DCUTR protocol at FOSDEM earlier this year, and also Peer-to-Peer Paris. So everything I'm about to present is a simplified version of that, so Max dives into the whole protocol way deeper than I will do. So check out these talks. I will send out the links to the slide later as well. So the motivation. What do we want to do? We want to have full connectivity among all nodes of a LibP2P network, despite NATs and firewalls. And as I mentioned, this was a common theme over the past few presentations already. The requirements would be no centralized infrastructure, should work over different transports, and it should nicely integrate into our libP2P stack. But maybe not all of you are aware of, so I will just briefly touch that. So NATs and firewalls. NAT stands for Network Address Translation, and basically maps your local IP address to a publicly reachable IP address. And firewalls, in turn, control the incoming and outgoing network traffic from your home network to the internet. And it does this by keeping track of packets that leave the network and try to come into the network with the so-called state table that you can see at the bottom. This is a little bit more involved than it's depicted here, but basically the most simple rule would be only let packets in from sources that I've previously sent out a packet to. So a state table entry would be, in this case, so if I try to connect to a server, the router keeps track of my source IP address from my internal network, then also the source port, and then the destination IP and destination port, and also which transport it uses. And then if a packet comes back, it looks into the state table and sees everything's fine, and lets the packet through. So what's the problem here in the case of a peer-to-peer network? So here we can see that we have two peers, peer A and peer B, on the left and the right-hand side, both of which are on their home networks. And in the middle we have the internet, and let's assume peer A wants to connect to peer B. So what happens? So peer A, let's say they want to establish a TCP connection, so peer A issues a TCP SYN packet. The packet leaves the computer of peer A, reaches the router A, and the router A updates its state table at the bottom, as I said previously, just with the source IP address and destination IP address plus ports. The packet gets routed through the internet to router B. Router B receives the packet, looks into its own state table and sees, well, I haven't sent out any packet previously, and it will just drop the packet because it doesn't let this through because there's no entry. And so how do we solve that? So as I said, so this will be, so how does hole punching work basically? We want to have a mechanism to connect both peers. And let's imagine that both peers, through a mechanism that I will go to in a second, could simultaneously synchronize with each other and simultaneously start a connection. So this would look as follows. So both peers would send out in the case again of a TCP connection, send out a SYN packet. Both routers would update their state tables. The packets would get routed through the internet. They cross paths somewhere over there. The packets reach the other routers. And since both peers have dialed the publicly reachable addresses of each other's routers, the state table entries would match. The routers would look into the state table, say, yes, that's fine, and the packets reach both peers. So this would be, in a nutshell, how hole punching works. So how does this work in the libP2P world, and mainly this DCUTR protocol that the people at libP2P have implemented? So DCUTR stands for Direct Connection Upgrade Through Relay, and this also takes it away. So we have a publicly reachable relay in the middle. And so when peer B boots up, it will detect that it is behind a NAT through a mechanism called AutoNAT, I believe. And we'll find a limited relay somewhere on the internet through another mechanism. And since Kubo version 0.11, all nodes are per default limited relay nodes. And limited relays only allow a certain amount of bandwidth to be shared, and also only a limited set of protocols to be routed through them. So peer B connects to this relay, and there's no hole punching involved because the relay is just publicly reachable. And peer B receives a multi-address that's a little bit, the font is probably way too small for you to read, so it's just a relayed multi-address. And through another mean, transports this multi-address to peer A, and peer A then also connects to the same relay and asks the relay, hey, can you forward traffic on behalf of me to peer B? And at this point, both peers are connected, but through a third party, through a relay. And as soon as peer B detects that peer A has connected to it through a relay, before we do anything of the hole punching magic here, peer B just tries to directly connect to peer A. So because this would be way faster than doing the DCUTR protocol that I will present in a second. And this would be called connection reversal, and only if this does not work, we will start this DCUTR protocol. So how does that look like? Let's imagine peer A is not publicly reachable in this case. So peer B sends out a connect message and starts a timer to measure the router time. So the connect message contains all the public IP addresses of router B. So no relayed addresses or anything, just the public IP addresses of its router. Then the connect message gets routed through the relay, reaches router A. Again, the connection is already established, so it gets through. The connect message ends up at router A, and the router A responds with another, the peer B responds with another connect message containing its own public IP addresses, and starts waiting for another message that I will get to in a second. So the connect message gets routed back, reaches peer B, and at this point, peer B knows the round trip time. So it has measured the time from sending out the connect message to receiving the response connect message. And now the magic begins. Peer B sends out a sync message, the second message type of this protocol, and again starts a timer. The sync message gets routed to peer A. Peer A was waiting for the sync message, and as soon as peer A has received that message, it tries to directly connect to the public IP addresses of router A, and peer B has waited half the round trip time to do the same. And in theory, both should start a simultaneous connection attempt to each other. And this is the hole punching here. So they send out a packet, the state tables get updated, the packets get routed through the internet, they reach each other's routers, the routers have the correct entries, and we are connected. So good times. Well, so that's the DCUTR protocol. And how do we know that this works in the wild? So this is just the theory behind that. So we came up with a measurement setup to that. Everything's open source. You can find it here. Again, I will share the slides somewhere, I believe, on the Slack channel or so. And this measurement setup consists of 3 different components. We have a honeypot, a server component, and a fleet of clients. The challenge here is basically we don't know where those peers behind NATs reside. Well, because they are behind NATs and we cannot find them, we cannot connect to them. They don't appear in the DHT because only DHTs, only publicly reachable peers will end up in the DHT's routing tables and so on. So how do we detect them? We use a honeypot, which is basically just another strong DHT server peer. And this honeypot announces itself to the network by crawling it continuously, and it just tracks the inbound connection. So when a peer behind a NAT tries to receive something from the DHT, it by chance, they will end up at the honeypot, and if the peers advertise a relay address, we just persist those those multi-addresses, and thus have detected a peer behind a NAT at this point. Then those peers that were detected get served through the server component that just exposes a simple gRPC API, and with just 2 endpoints basically. So you can query a peer that is behind a NAT, and you can track the result if you've performed the hole punch back. And then it's two different client implementations that just talk to the server. So these clients live on your MacBooks or on your laptops, and they request a client to hole punch from the server. Then the client performs this DCUTR dance with another peer and reports back the result, if it worked out or not, or some other things. This is the architecture diagram of what I've just explained, basically. So again, we have the honeypot. The honeypot slowly walks the DHT, so it's a very stable peer. And by slowly walking the DHT, we announce ourselves, or the honeypot announces itself to the network, and we just hope that the honeypot gets inserted into the routing tables of other peers, so that a client peer behind a NAT requests something from the DHT, they get routed to the honeypot, and then we have basically the chance to detect some peer, DCOTR capable peer behind a NAT. And then you can see the honeypot saves the relevant inbound connections to the database, and then those entries get served through the server component, and then we have a lot of clients, well, not a lot you will see, but a few clients deployed that then will request those peers from the server and try the hole punch on the right-hand side. All of that is monitored, so we have a nice Grafana dashboard if you want to check that out, if everything's up and running and fine, and the results, the success rate, and so on. Also quite interesting. So now, the fun part. So what are the results? Does it actually work? First of all, so I mentioned that the Kubo version 0.11 has enabled the limited relay capabilities per default, which are a requirement for this DCUTR protocol to work. Then the DCUTR protocol itself, this hole punching, was enabled per default with Kubo 0.13, and this was released on June the 9th. And this is the red line there, so we can see that people are upgrading to this new version and then thus benefiting from this new capabilities here. Also, if we take a look at the honeypot connections, these are so you have the time on the x-axis and the incoming DCUTR capable peers on the y-axis per day. You can also see that people are updating and that this DCUTR protocol gets more and more deployed in the network over time. As I said, we have a fleet of clients. Well, again, it's not a big fleet right now, so we have 8 different clients deployed, or 7 different clients deployed so far. And each of those clients requests peers to hole punch and then report back the results of that. And this rather messy graph shows how many hole punches each client has performed during the last months. The axis on the left-hand side goes from 0 to 2,500. So it's around 1,500 hole punches a day per client, and each of these different colored lines is a different client which was active during different times of the last few months. Each hole punch itself can end up in different states. So the server spits out multi-addresses of those clients behind NATs, which are basically these relayed addresses. So if this is a very ephemeral peer that just goes online and then leaves the network again, it's very likely that if the client fetches this peer, 5 or 10 minutes later, that we are not able to connect to this peer. So this is the no connection outcome. So at the x-axis, we have these different outcomes that a hole punch could have, and then just the share of all hole punches on the y-axis. And the no connections on the left-hand side, so we can see that actually many peers that we detect from the hole punch, we are not able to connect to through this relayed address. Then there's this no stream outcome, which is quite interesting. This means that we were able to connect to the other peer, And then the other peer needs to initiate this hole punch, the DCOTR protocol, but it just didn't. So it didn't open this DCOTR stream. So the client was sitting there, we were connected through the relay, but then nothing happened. So the stream was not open. So this is the no stream outcome here. Then connection reversed means we were able to connect to the other peer through the relay. The peer tried to directly dial ourselves, and this actually worked out. So this is also an outcome here. And then the actually interesting ones where we performed the hole punch, the DCTR protocol, the message exchange, and then we have the outcome of failed. So it didn't work out, or success, we were able to connect. We were able to establish a direct connection. And at the end, this just applies to the Rust implementation. This is a canceled state, which means the Rust client was served a quick connection, and quick is not supported on Rust yet, so they canceled the hole punch on the client side. So this is also a little bit messy. So I think this is, so we will focus on this part. And this is probably the crucial graph here. So this is the success rate of this hole punch DCOTR protocol. We have the time on the x-axis again, and then just the success rate. So it's basically the number of successful hole punches divided through the actual number, the total number of hole punches performed per day. And each line is a unique client, and as I said, they were deployed and online for different times during the last months. I gave each different client a different fruit name, so just that we can tell them apart. But I can tell you I am the orange line there, and this graph shows that my client has a success rate of around, well, slightly less than 80%. So if we do this DCOTR protocol and this exchange, we have an 80% chance of ending up with a direct connection, which is, I think, pretty amazing. So, yeah. Then there are some interesting things going on. So you can see the red line that goes down at some point. And this is a client that was running over a VPN network. And I think this needs further investigation why the success rate is way lower or significantly lower than the others. The other lines are roughly at the same levels, but the VPN, the client in the VPN network is, well, yeah, let's say 20% less successful than all the other clients. So this may be something to look into. And then there's this, do I have the cursor here? Well, I will just show it here. Yeah, this little bit here. This is just a brief moment where a Rust client was deployed. And yeah, we need to look into that, why this, the success rate of the Rust client is so low compared to the other clients. All the other clients are Go clients using the Go implementation. We need to look into that at this point. And another outcome, I think, for protocol improvements at this point. So I didn't tell you when this hole punch dance, so this back and forth of the connect message and sync messages didn't work out. We just try again, and in total 3 times. And if we take a look at the successful connection establishments, how many attempts we needed to actually establish the connection, we can see that in 97 or 98% of the cases, it worked within the first attempt. And this means if it doesn't work with the first attempt, we can just stop the protocol and not try again, and be reasonably sure that the connection cannot be established at this point. So this could feed back into a protocol improvement at this point. Then, with which transport do we end up when we did after we did this hole punch DCOTR protocol? So we have the transports TCP and QUIC on the left-hand side, TCP, and QUIC on the right-hand side. And if we take a look at the so this is the fraction. So on the y-axis we have the fraction of successful hole punches and how many were successful using the TCP protocol versus the QUIC protocol. And there are also, again, a couple of interesting things going on. On the TCP side, you can see that the VPN, so the client that's running on a VPN side, basically cannot establish or cannot hole punch over the TCP protocol. This is why the red bar is so low there and almost 100% on the quick side. And on the other hand, the Rust client has a 100% success rate on TCP in case there's a successful hole punch, and a 0% success rate on quick, which again is quite So quick is not implemented in Rust, so it cannot work. But again, the VPN part is interesting to me, so it would be great to find out what's going on there. Then we could, so there, as I said, there are so many relays deployed already, so people are taking up the new versions, and could we actually improve the success rate by choosing the relays depending on the RTT to the relay? So we can imagine if I relay the hole punch synchronization through a relay that resides, let's say, on the other side of the globe, in Australia or New Zealand, I think network jitter and so on could impede with the round trip time measurement and so on, and thus limit the success rate here. So this is a CDF of the round trip times for successful hole punches. On the x-axis we have the time in seconds, and on the y-axis how many hole punches that succeeded actually had this specific round trip time. And I don't think I don't think it's relevant to look at the exact numbers here. So just compare it with the failed hole punches. Okay, also hard to see. This is just everything added up. So in this graph, we can see that in the failure case, the round trip time tends to be slightly higher. So this means if we have a slightly higher round trip time, it is a little less likely that this hole punch protocol succeeds. But this is, I think, a very tiny difference here. And if we take a look at all the different clients that were deployed, this is these are box plots, and the takeaway would be that they basically look all the same. And so there's no clear, from my opinion, no clear correlation between round trip time and the success rate of the hole punch. And then I think the last graph, plenty more graphs, but let's take this one as the last one. So this is the protocol errors by agent. So this is something that I found out when so I just took a look at the error cases for hole punches and grouped them by the different agent versions. And we can see that this no stream error or outcome that I talked about previously, so where we were able to connect to another peer, but the other peer just didn't open the DCOTR stream, almost always happens with this Rust IPFS implementation. And yeah, I think, I'm not sure which implementation they use, which DCOTR implementation, but this is, I think, something that we need to look into. So this just shows we were able to connect to a Rust IPFS node, but the Rust IPFS node did not start the stream and this DCOTR protocol to us, although they advertised to support it. So would be good to look into that. Okay, I have plenty of more graphs, but let's leave it at that. The next steps would be for every one of you to sign up and run a client. So scan the QR code. You can see that if you're on a Mac, you will download a system tray icon or like a menu item there at the top right-hand corner, which will just connect to our server, get a peer, and the peer will be hole punched, and then the outcome will be reported back. The system requirements, so this has a bandwidth impact of around, let's say, your two websites, you open 2 websites every minute or so. So this is probably the bandwidth requirement here, or maybe 1 website. And on my machine, it uses around 2% of CPU, but 100 megs of memory. So that's not so good, but yeah. So I really appreciate if you signed up. We want to have a hole punch month. So during December, so we try to attract as many peers as possible, as many people as possible to run this client. Also on Linux, there are binaries available. Please sign up. And as I said, we want to have a hole punch month where we have as many clients as possible running to increase the data foundation for all the measurements that we did and all the graphs that I showed to you. And with that, Thank you very much.